Hey, welcome back. In our last few lessons, we've been working hard on analyzing the graphs of functions. We've seen how a graph visually represents the relationship between inputs and outputs. And that's what a function is, right? A relationship between inputs and outputs. More specifically, where every input has exactly one output. But how can we describe a function algebraically without its drawn graph? Let's revisit the beginning of our unit and take another quick look at our function machine. It takes an input, processes it using the function's rule, and then finds the output. We might have had a function rule that told us to take the input and add 1. So an input of 2 would give an output of 3. An input of 4.5 would give an output of 5.5. And an input of 100 would give an output of 101, and so on. But now we know that the variable x can also represent our inputs. Think back to what we know about translating expressions. How could we write this rule as an expression instead? Yeah, x plus 1. We can actually use this rule written as an expression to write our function algebraically using what's called function notation. Now, notation just means a way to write or represent something. So function notation is a way to algebraically represent a function as an equation. It's kind of like giving the function a name and describing it in a short and clear way. Now, let's use that example we were working with on our function machine, the one with the function rule of x plus 1. I'm going to call that function f. That function f can be written using this notation. So let's see, what do we have here? We have the name of the function. Typically, functions are called f, g, or h, but it can be any letter. Then we have the input variable. So that's the variable that represents the inputs, x. We say this part as f of x, which just means the function f using the inputs x. F of x is equal to our function's rule that is used to find the output, which in our example was x plus 1. So we can say this whole notation as f of x equals x plus 1. All that's saying is I have this function named f, and it uses inputs of x. And to get an output, I'll have to add 1 to each input of x. Using function notation gives us a short and sweet way to describe the function we're working with without having to draw up a whole function machine. And from there, someone can create a table of values, a list of coordinates, and create a graph. Let's practice reading another function's notation. How about this one? What does this say? What information is this function's notation giving me? Well, firstly, I would read this aloud as g of x equals 5x, or 5 times x. So I know that the name of the function is g. And the variable that represents the inputs is x. And lastly, the rule of this function is to multiply the inputs by 5 to get the outputs. Okay, great. So if we were asked to find g of 3, what might you think this is asking me to find? It's asking me to look at function g and, using the input of 3, find the output. All right, well, we know the rule for the function is to multiply inputs by 5 to get outputs. So I'll go ahead and input 3, or substitute 3 in for x, and we get 15. So g of 3 is 15, which means that if we input 3 into function g, we get an output of 15. Pause the video here and find g of 6. Here I'll input 6, or substitute 6 in for x, and we get 30. So g of 6 is 30, which means that if we input 6 into function g, we get an output of 30. The work we've been doing here of finding the output when given an input is called evaluating a function, specifically evaluating a function algebraically. Let's keep practicing evaluating a function algebraically with an example problem. Given the function m of x equals x squared plus 2x minus 3, find m of 3, m of negative 3, and m of 1/2. Pause the video and give these a try. When finding m of 3, 3 is my input, and I'm trying to find its output. So I'll substitute 3 for x wherever it appears in the function, and simplify to find that m of 3 is equal to 12. That means that when I input 3 into our function, the output will be 12. When finding m of negative 3, I'll do the same and substitute my input of negative 3 anywhere that x appears. Now, be careful with negative numbers and exponents. Here I'm going to square the whole thing of negative 3. Then I'll simplify all of this and get an output of 0. And same goes for an input of 1/2. When simplifying this, I'm going to square the whole fraction 1/2 and then continue simplifying to get negative 7/4 as the output. Or if you prefer working with decimals and changed all of these 1/2s to 0.5, you will still get this same answer, but it'll just be in decimal form. And negative 7/4 in decimal form is negative 1.75. Nice work. So far in this unit, we've been working a lot with the graphs of functions, and we can also evaluate functions from their graphs as well. Let's have a look at another function, function h. Here, we've been given the graph of function h. Oftentimes when working with a graph of functions, you will see the function name somewhere near the graph, like the h you see here. The graph also gives us the function's notation. Pause the video here. How would you say this function's notation out loud? We would say h of x equals 2x plus 3, or 2 times x plus 3. What if we want to find h of 1? How can we do that? Well, we have the function notation, so we could find it algebraically like we did before, but since we have the graph, we can also find it graphically. So let's give that a try. Finding h of 1 means that I want to look at the function h and find the output using the input of 1. So let's look at our graph. If we input 1, what is our output? 5. Great. So h of 1 equals 5. Pause the video here and check your work by finding h of 1 algebraically using the function's notation. After substituting in 1 and simplifying, we find that for an input of 1, we get an output of 5, which checks out with our work when evaluating h of 1 graphically. All right, pause the video one more time to find h of negative 4 graphically. And if you want to check your work and get more practice, go ahead and find it algebraically as well. Finding h of negative 4 means that I want to look at function h and find the output using the input of negative 4. So let's look at our graph. If x is negative 4, the output is negative 5. Great. So h of negative 4 equals negative 5. And evaluating h of negative 4 algebraically gives us the same thing. Awesome work. Let's practice evaluating a function graphically with an example problem. Here is the graph of function n. Pause the video here and find n of negative 1, n of 0, and n of 2 graphically. When evaluating n of negative 1, I see that when I input negative 1, I'll get an output of 8. So n of negative 1 is 8. When evaluating n of 0, I input 0 and get an output of 3. So n of 0 is 3. When evaluating n of 2, I input 2 and I get an output of negative 1. So n of 2 is negative 1. Really nice work. In this lesson, we've seen that function notation is a way to algebraically represent a function as an equation. We've learned how to evaluate a function algebraically by substituting the given input into the function and simplifying, and we've learned how to evaluate a function graphically by using the given value of the input and finding its corresponding output on the graph. Once you're all done watching this video and completing the guided notes, check out the additional practice in your PDF. It'll prepare you for the practice game that follows. Good luck, and I'll see you next time.